Okay, this is lab number 6 and this is our first example. Here we will see two things. The first is the normal SIMD, pragma OMP SIMD clause, and we will see another clause, pragma OMP declare SIMD. So to test this thing, we have created two functions. Work of these two is similar. That is a returning x minus y, x plus y's division. We have added on this thing so that no zero answer could arrive for any reason. So we have two functions, a simple function and another is a vector function. We have used attribute no inline before both functions. Purpose of this is it actually stopped the compiler to remove this code. As this code is not being used anywhere else, means its values are not being used anywhere else, or we haven't printed these values as well. So compiler will compile the total program. So it actually check whether this result is not required here, and as it is not being printed anywhere else. So compiler considered this code as red hat code and it could be removed, and automatically the functions that we will see later on, the values that are being calculated in them, they are not also being used. It might possible it could be considered as a dead code. So compiler could not run that code. That's why we have used these two attributes of no inline. And more than that, a single function is of OMP declare SIMD. Purpose of this is the way we have used a normal SIMD in the last session. What we have done that we have distributed the loop into the parallel breakups with the help of SIMD. Now with this code, instead of loop, we are also telling the function itself that you will going to be distributed using the SIMD. The benefit of this is that whenever we will be calling it from the main function, let's move on to the main function first, where we have taken the array size like this. We have three arrays over here. We will initialize a and b value via loop. You can check it out. It will come like this. And we will store the result in C. After that, we have done the same task like the lab number 5. Start time, symbol time, and the vector time. And we have created a dummy sum variable. Its purpose I will going to explain soon. Let's check out the first case. We are calling here a scalar function inside the SIMD loop. Here we have noted down the time start. First loop run, that would run on the number of iterations. We have taken 10 million iterations for telling the difference. And then we are using pragma OMP SIMD. Means that we want to execute this loop in parallel. And in that loop, we are calling a simple function, as we are talking about the scalar function here. So we are actually in the SIMD loop, but we are calling a simple function in which the declare SIMD is not being used. Means that function that we are calling is not of SIMD, it's a simple function, but the loop only belongs to SIMD. After that, if you will just calculate the value of C, then this part of the code will not run, as the C values are not being used anywhere in the code. For that, we have used a dummy code by ourselves. Its purpose is it uses a dummy sum variable here that we have initialized with 0. We will going to store the value of C in that. You could use any normal value of C. Here we are using the 0th index C value. It actually does what? It actually runs this code. Otherwise it could be ignored by the compiler. Similarly, here we have another function, case 2, in which we are using a function, SIMD function. And here we have already calculated a simple time value above and also printed out the dummy value. So actually the dummy function performing in the code, it could calculate the C value as well, also calculate this value as well and print it. So this loop is actually needs to run. So here we are doing the same work, resetting the dummy value. We'll again start the time. We have the same loop, we have the same function, but just we have change of the vector function instead of scalar function. So now we are using the SIMD declared function, that is the vector function. Same work being done for the dummy variable, and we have taken out the time, we have applied the check, and we have ignored it. And we do not need to just follow up this value. It will just use for printing. So this value is not of use. And then at the end we are printing the results, where we will having the scalar function time and the vector function time, and we have also printed out the speedup value so that we can compare. Now let's compile and run this code. So running task 6, example number 1. As we have set the 10 million iterations, it takes the time, but it's necessary to put them. If you will take the small value of iterations, so most likely there would be no difference to be observed. So that's why I've taken the 10 million values of iteration. Don't worry if your code is taking high time. So initially our dummy value have been printed out. both the functions have been given this value and both the functions have ignored the dummy value, and it have printed out the result value as well. A scalar function have been taken 18.5 seconds almost, whereas the vector function have taken very small amount of time comparative to scalar, that is 4.06 seconds. Almost 4.5 times speed up value arrived. The reason is that where we have declared the SIMD, that function is also running in parallel and its loop is also running in parallel. You can also see that here we have used the loop in parallel, and then in that parallelized loop, in that this function is also being called in parallel. So here we are getting the multiple levels of parallelism, due to which the speedup is increasing, the code is running fastly. In scalar, the only loop of ours were running in parallel, that is was being called in serial fashion. So that's why it has taken a lot of time. Okay students. Okay, now this is example number 2 of the lab number 6. Here that we use the pragma OMT SIMD, we will apply at the different places before the loop and after the loop of this OMP SIMD to check that which method is actually efficient, which gives the better result. And here we will also study a collapse clause that will help us. Starting with the standard namespaces. In our main function, we have initialized n value whose size is 128. We could take small value of n, but we have taken this value because if you have a fast processor, then you would not get any noticeable difference. After that, we have initialized 3 2D arrays, A, B, and C. Both would be of 128 by 128 dimension, that is A and B, and the C would actually store the result of A and B. Initially, we are initializing the matrices for A and B. So they will store like this, as they are 2D arrays. So obviously the structure would be like this. Here we are starting from 1, here we will start from 2, and C is initialized with a 0, as we will store the result in the total matrix. Here we have done the same task of the dummy variable. If we will not do this task, then total calculation would be ignored, whatever we will perform later on, as the C variable is not being used anywhere else in extra code. You can also print it out, it will actually take the work out, but we are also calculating it, that we can margin and calculate the extra difference, because just printing will not give you a noticeable difference. We are doing the same task starting with clock start. After that, we are applying the SIMD on the outer loop. As already discussed, this is an inefficient method. It has some issues, we will see it. We start a clock. Here our iterations are 1 million. We have not taken the 10 million as previous example. They were consuming too much time, that's why. For case 1, we have taken the pragma OMP SIMD, applied on only outer loop rather than applying on the inner loop. Now in C, there is a problem. When we are storing our array, it is basically being stored row-wise. Like A00th element will be closer to A01th element, but A00 would be very far from A10. Obviously, you are getting my point. Means it's n slots away. Like we have n is equals to 128. So these iterations will be running A01, A02, all the way up to A0127. And after that, A10 will arrive. That is the reason if we are applying the SIMD on the outer loop, so we are applying and trying to perform this step, means it's actually picking out after every 128th value. Obviously, this would be time consuming. Calculation is similar, that we are calculating the C value here. This extra step is actually I have done basically for dummy variable. Its work is to actually calculate the value of C and store it into the dummy variable for the 0th index. So that C would going to use, and it will show the difference in output of time. Otherwise, this whole code would going to be ignored. This was our case 1. This is actually inefficient because its output will take more time comparatively. Still, because we have little iterations, we do not have much more data. But as soon as you will increase the data, time will increase exponentially. Similarly, we have taken out the outer time over here. Then let's start the second case, where we have used the SIMD inside the inner loop, which is already a standard that we were being using normally. For this, we start the clock. 1 million iterations being taken again. Now we have 2 loops already told, n by n matrix. Rather than to type the SIMD over here, we have applied it inside the inner loop. The reason is the outer loop value will remain 0 and the inner loop will get increment. The benefit of it that A00 is closer to A01 and our calculation would be efficient and processor do not need to skip the memory locations a lot unless the loop iteration is not getting changed. When there will be 1, then we will need to change the memory location, means for next item. So this is the standard way. Here we are doing the same dummy variable work. These two steps have been extracted, already told. This will actually efficient our result. And then we have taken out the inner time over here. And our third case is to use collapse. Collapse actually flatten the calculation. Meaning of the flatten is that it combine both the loops and create a bigger loop. Our clock is starting from here. Again, we have taken 1 million iterations. After that, on outer loop, which was an inefficient method, but we have applied a collapse keyword. And then we have told that two loops need to be combined inside collapse. So this loop and this loop will collapse to. This clause will tell the compiler to treat the nested loop as one giant single loop whose dimension is n by n. Here it would be 128 by 128. Let me correct it. So this calculation, we have done the same task over here. As we are calculating C in every iteration, we have added on the dummy variable and we have also incremented that variable so that this code will run. Otherwise, again, it would be considered as a dead code. After that, we have given the collapse time as well so that we can get a smart comparative answer. At last, we have printed out all the things: outer loop time, inner loop time, and SIMD collapse time. Ideally, what happens that outer loop is very slow, and then inner loop times arrive, and then collapse times, efficient times arrives. But in most cases, inner and collapse are almost similar. And we have applied a dummy ignore check, so that dummy variable we're going to be used, and compiler will get time to check. Let's run this code and compile it. Task 6 example2.txt. Obviously, it will take time as n size have been increased from 64 to 128. Iterations were going to be increased. Now we can observe over here, not as noticeable difference, but SIMD outer loop at 3.63 seconds. SIMD inner loop is about 3.58 seconds. SIMD collapse greater than SIMD outer loop, but 3.62 seconds. Actually, what happens? The more time would actually consumed by outer loop, and these two actually depends. Sometimes collapse give almost similar time to the inner loop. Sometimes it will give more than inner loop. This time it's actually given a very closer value. Sometimes it give smaller value than the inner loop. It depends. Actually, this will give answer different at different times. Let me check it again after deleting this output file and then recompile the file and then rerun the file. Now we can see that in our second iteration, outer loop is 3.64 seconds, inner loop is 3.568 seconds, and SIMD collapse is running 3.574 seconds. This time these two values are very closer and the outer loop is far away. It depends on how your iterations are running and how your processor is behaving, and then however we will increase the value of n, we will get the noticeable difference as the outer loop time will exponentially increase. If we will increase the value of n, then we will get the noticeable difference. Let me try this after converting it to 256, as it will take a lot of time in compilation. So as this takes a lot of time, that's why I avoid this increment. I wish it could run, otherwise the 128 value would be our last value. 256 locations are more enough. Oh, we got the result. Here we can observe the outer loop have 14.483 seconds, inner loop it's at second 14.386 seconds, and collapse one similar to outer loop, but again outer loop have taken much more time, inner loop have taken comparatively very lower time, and the collapse, just like the first example, is a bit smaller than the outer loop. So again, it depends on the processor and depends on its working, and how this optimization is working, it actually depends on it. So in depth, how it works, the compiler actually performs it. Okay, students,